Welcome, my fine Patreon folks. This is the Ethereal Mechanics Experimental Series 01, the CRIM, where we're going to validate the new induction model, also known as the inertial force model of new electromagnetism V5. And we're going to do that with a current ramp induction metering circuit. And this is for Patreon only, part 1 theory and a little bit of the design. So in this video, we're going to talk about what the current ramp induction measuring circuit is, what it does, a little of the theory. We'll go through a little bit of the preliminary design and do some parts selection. And I'll show you where I am as far as the construction of the setup. So the reason for last week's video is I realized while I was making this video that it's not wise to talk about how to measure an inductor until you first explain to people what inductors are and what they do. And that if you go search for the tag EM04_02, you're going to find the video of how inductors really work. Inductors essentially just a coil of wire. Really, it's all they are. But one of the problems in measuring an inductor is that an inductor is more than an inductor, but it's mostly an inductor. Because these loops of the coil are very close to one another, there's going to be some capacitive coupling between the loops of an inductor. Okay, so instead of just a pure inductance, really what we're measuring here is you could take each little turn of the loop, and let's say there's 10 turns in the loop, so you take L divided by 10 and you put that there, and then you have a little capacitor that talks about the capacitive coupling between that turn. So each one of these little things represents one turn in the loop. That is a way, one of many ways, to model an inductor more closely to a real inductor. Okay, so the problem is this capacitive coupling is going to interfere with us validating the models, because the models are computing the inductance based on pure inductance. Later on, we're going to improve the software so it'll do everything. It'll do the capacitive coupling, it'll do the inductive coupling, and therefore we should be able to use the Agilent LCR meter with the new software that we're going to develop in the future once we validate first that the inductance model we have is good. Okay, we got to do one step at a time, baby steps. Let's validate the model for inductance, and then we can improve the software so the software will simulate the entire setup for everything involved and see if we can't get exact results with the Agilent LCR meter. So one of the ways to defeat this capacitance is to understand how the capacitance works. The capacitance, this C represents capacitance, will transfer current between the different loops of the wire based on the voltage change between the loops of the wire. This dV, dt, for those who don't understand differential mathematics, this means the change in voltage as a function of time. The change in voltage as a function in time. So you take your voltage change, multiply it by the capacitance, and that'll be the current that is coupled from one loop to the other. Some people call this displacement current. I just call it capacitively coupled current, whatever. Okay, and so the way to defeat this is to take your inductance measurement by keeping the voltage constant. If you keep the voltage constant, not changing over time, there'll be no contribution from this I, and your C will not affect your measurement. And that's how you can measure the pure, well, closer. We got one other thing we're going to talk about, but that's one step to getting closer to measuring the pure inductance. So that way here, what we have to do in order to measure this is we want to keep our voltage constant, and we want to keep of course, the inductance is going to be constant, and therefore the change in current over time will have to be constant. This constant change in current over time is going to be a voltage ramp. So in other words, if we put a voltage ramp, uniformly changing like a nice straight ramp, that will keep a constant voltage across the inductor, which will then allow us to measure it without affecting the capacitive coupling. And the way we're going to do that is what's known as the current ramp induction measuring circuit. This I developed in the 1990s. This is not new, but we're going to improve on it drastically over what we had in the 1990s. Okay, so essentially what's going to happen in this circuit, here's our inductor under test down here. we're going to have a control circuit that's going to go from 0 to a constant voltage here. Well, no, let me rephrase that. The control circuit is going to control the base of this N-channel MOSFET transistor. And what that's going to do is that's going to affect the current through the inductor such that the voltage, it's going to try to keep the voltage. So it's going to, their circuit that's controlling this is going to monitor this voltage to keep this voltage constant. And because it's trying to keep this voltage constant, the current that's going to be supplied here, it's got to come through the 12-volt supply through the transistor. And that's going to cause a constantly changing, a uniformly changing, a current ramp is going to occur. In other words, the current's going to increase at a constant rate. Okay, and we're going to measure that current through a resistor by measuring the voltage above and the voltage below the resistor. And so, in fact, we're going to measure that current ramp as a voltage ramp across this resistor. This is essentially a current sense resistor. Okay, therefore, this current ramp is going to be constant because we're going to apply a constant voltage step to the inductor divided by the inductor. Now, we're getting rid of the minus sign here because we're worried more about the signs aren't really that important. We know what the signs are going to be. We're more worried about the quantity. So I'm going to be dropping out minus signs here. Don't mind that. It's going to work out because it's just a matter of the direction of stuff. We understand what the direction is, so we don't really care about the minus sign here. Okay, and so that current step, because it's going to be a constant, once we apply the step voltage, okay, so there's going to be a point in time where we're going to apply the step, and that current, this control circuit is going to cause this voltage to go from 0 to a known value and keep it there as constant as it possibly can. That's going to cause the current to continually increase through the inductor, which will increase through the resistor. And because this is a nice uniform constant slope, the di dt can be replaced with delta I delta t, okay, which will be a constant because this is a constant. Okay, now because we're going to measure this current ramp with a resistor, we're going to, and because voltage is I times R, we're going to multiply this by the resistance, and that's going to give us a voltage across the resistor. Okay, and because delta I, and then what we can do is we can replace our delta I delta t with V step over L, and this will then be our voltage ramp. So this represents the voltage across the resistor as a function of time. That's time. That should be a little lowercase t here. That represents the period. Okay, so what's going to happen is our control circuit is going to drive the gate of the MOSFET in such a way to keep a constant voltage at this point here. This constant voltage is going to require the transistor to pull more and more current from the positive 12-volt supply through the resistor in order to maintain that voltage as the inertia across the inductance decays. Because we're keeping this voltage constant and the inductance is constant, that will lead to a constant di dt, which can be replaced with delta I delta t because this is going to be a constant slope, a nice uniform changing slope. A change in current over the change in time. Change in current over a change in time is going to be constant. Okay, and so this is where we get the term V step, because our control circuit at a certain point in time is going to change the step voltage from 0 to a certain step value, and it's going to hold that value constant. So our V step is going to be a constant value. That's what the V step is actually going to be here. Okay. And then, so the way we're going to measure this current ramp is we're going to measure it with an oscilloscope across the resistor because that current has to go through the resistor. And so the voltage drop across this resistor is going to be the current times the resistance. So the current at a point in space at time t, big T, will be the slope of the current ramp times T times resistance. That will be the voltage at R as a function of T. I should have put a little lowercase t there. Okay, but because we know that the voltage ramp is going to be proportional to the voltage step over the inductance, we can replace this with that. And this is our voltage across the resistor as a function of time. Okay, now that we have an expression for the voltage ramp that we're going to have across this resistor, what we want to figure out is, some of the design design parameters or design limits. So one thing we're going to put in is a 12 volt power supply limit. We're just going to limit this to 12 volts. 12 volts is a pretty regular normal power supply range. Okay, typically, so when we do this step, we usually have 1/10 of a volt across the inductor. Okay, so if we have 1/10 of a volt across the inductor, well, that leaves 11.9 volts of available margin here. Okay, but for growth, what we're going to do is we're going to allow 1/2 a volt across the inductor in case, we've got these really big inductors where we need more voltage because they got a lot of internal resistance. So we're going to allow this to go up to 1/2 a volt. So that'll leave 11.5 volts of margin here. Now we're going to take up more of the margin, because if we allow this resistance of this inductor to be up to 1 volt, well, we might have, a significant voltage drop across here. And there might be a voltage drop across there for other reasons. So what we're going to do is we're going to say that we're going to keep the voltage ramp across the resistor to 10 volts or less, just so we have a lot of margin down here for how we're going to change things up. That'll also allow us to change if you want to change to a different type of transistor, yada, yada, yada. And 10 volts is a pretty good voltage drop for this. And it'll also allow for any little voltage droop in the power supply, which I'm sure we're not going to get much of. Okay, so that begins some design limits then we can then use to select our parts. So what we have from our experiment, we go through for the experimental data that we are going to reproduce, and we go through all this data. We find out that the smallest inductance we measured was about 77 nanohenries. Okay, so what we're going to do is we're going to have our design lower limit for our CRIM to handle 40 nanohenries, just to go a factor of 2 beyond that. Okay, and if we also look in here, we see that our maximum inductance that we had was about 1100 or 1200 nanohenries. So we're going to make our design target max at 2000 nanohenries. Now, I think with this circuit, we can go to very far beyond this. But, we'll cross that bridge when we get to it. But we should be able to go much higher than this. Okay, so the equation we developed for the voltage ramp, and let's work it backwards to find out what will be the ramp time at the minimum inductance. Because the ramp time, how quickly that voltage can span 10 volts, is going to affect how many samples we need and so many other factors. Okay, and so if we do that, if we take this equation here, let's isolate T and R together. So we divide both sides by V step over L. That gives us our TR constant, because we haven't decided what size resistor we're going to use. So our slope times our resistance is going to, affect our thing. So now we have these values known here. We're going to plug them in. And that means our TR value has to be 4 times 10 to the minus 6. Okay, the maximum sampling rate of the Siglent scope with 4 channels is 2.5 gigasamples per second. We want at least 100 samples. That means our T ramp has to be about 40 nanoseconds long. So if we take this TR, divide by 40 nanoseconds, that gives us a resistance of 100 ohms. Now, we have done 100 ohms in the past. And I've decided in the past we want more than 100 samples. Let's try to double the number of samples. So, because one of the problems we have is when the ramp, when you apply the ramp, we did this in the past with an op amp, that ramp doesn't go perfectly up to a voltage and then stop and then remain continuous. what we get is a little bit of a ring before it stabilizes. And we can't take our measurement until after it stabilizes. And so what we end up doing is we end up missing a lot of our available ramp time and ramp space because of that ring. So we want to make our ramp last a little bit longer and allow us that this ring could settle a little bit, not take up as much. If we make this ramp longer, this ring won't take up as much. So we want to extend the ramp by at least a factor of 2, and that's why we're going to drop to 40 ohms as our resistance for our crim. So with that, let's look at our design parameters now. Our supply is 12 volts. Our V step is going to be 0.1. Lmin and Lmax are the values we determined from the data. These are a factor of 2 off the data. We have chosen a 40 ohm ramp resistance. Our voltage ramp, we're going to look for a 10 volt. Okay, that should be 10 volts, not 10 ohms, sorry. The time of our ramp is going to be 100 nanoseconds for the minimum. For the 2000 nanohenry, that's going to be 5 microseconds. Very easy to measure something that big. The problem is measuring as we get smaller and smaller. So we're more concerned about the low end of this. So at the low end of this, the number of samples we're going to be able to put on that 100 nanosecond ramp is 250. And we'll find out that's not too bad. Now, what we're looking for as precision goes, the precision that we had with the data using the Agilent LCR meter, the precision, the match between the measured and the theoretical was 2%. So in this data series, I want to take at least a factor of 2 bite out, a factor of 10 bite out of that. And so our precision that we're looking for is 0.2%, okay, which works out to 2,000 parts per million. I think we're going to do a lot better than that, but at least this gives us a starting point. So let's now figure out the resistor that we need for the crim. And one of the things we definitely need is we want a non-inductive design. And this is actually a selectable parameter. In other words, we don't want to measure the inductance of our ramp resistor. We want to measure the inductance of the inductor. So we want a resistor that has a non-inductive design. Okay, now what's the power handling of that resistor? Well, the worst case power handling would be if the circuit were completely stuck open because we made a software bug and didn't turn it off. We don't want the resistor to burn up in that case. And so the power that's going to be, the worst case power that's going to be across that resistor is the voltage squared divided by R. And so that's going to be 12 volts squared divided by 40 ohms is going to be 3.6 watts. So we want a minimum, as a bare minimum, we want a resistor that can handle 4 watts of power. Okay, in reality, we could probably get away with a lower power resistor if we kept the duty cycle. In other words, we only measured it like every few seconds or something like that. Okay, the problem again is if we have a mistake and the circuit's stuck on, the resistor is going to burn up. So we want a minimum of a 4 ohm resistor just to take care of the fact that it may be stuck on. Okay, the important thing is temperature stability. Okay, because we're going to be driving this thing with watts of power. Okay, we don't want the fact that the resistor is heating up to affect its resistance that much. And that's why we're probably going to go for a higher power resistor than 4 watts, because a higher power resistor will keep cooler and not be as affected by its temperature change. Okay, and then we're going to shoot for no more than a 20 degree per C change in temp. I pulled this completely out of the air. I don't think we're going to get near this, but this is my upper limit. And so if we're looking for 2,000 parts per million tolerance, okay, divided by 20 degrees, that means we're looking for a resistor with a 100 parts per million per degree C temperature stability coefficient. This means that the resistance won't change more than 100 parts per million for each degree C of temperature change. Okay, I'm pretty sure we're going to do a lot better than this, but this gives us a nice limit that we'd shoot for, that if we can't do better, I'm sure we're going to do better than this, but this gives us a value to beat, as you want to say. In other words, we need to meet this to meet our 2% tolerance in the measure, or 0.2% tolerance in the measurement. Okay, so we're going to run off to DigiKey and show you how to select the resistor. Okay, now we're going to go look for the resistor that we're going to use for the CRIM circuit. So we go to the DigiKey page. I like the DigiKey search function for finding parts. Sometimes they find for me a part I already have, which is great. I don't have to go buy it, but there we go. We want resistors. Okay, now I already know that chip and surface mount resistors are not going to have the power handling capability that we want. If they do, they're going to be wickedly expensive. Okay, so we're going to go look through hole resistors. And the first thing we want to do when we get on any page like this is their search. It gives you lots of columns, helps select down the resistor. They have 500,000 different results under through hole resistor. First thing we want to do is knock down and look at things that are in stock and things that are active. So there you go. We've gone from 500,000 to 25,000 about. So we're going to apply all. Next thing we want to do is select the resistance. Now we don't want to put just 40 in. We want to give ourselves a little bit more options here. So we're going to put 35 to 45. It says 14 because that says milliohms here. We want regular ohms. Okay, we want to apply that. Now, I'm not too crazy about the tolerance. That's not really a big deal for us because in the end, we're just going to measure the resistance with a precision multimeter. And so we're going to eliminate the tolerance or the uncertainty that way. So we're not going to spend a lot of money on a high precision tolerance resistor. What is more important to us is the two items involved with the stability, which would be the power handling and the temperature coefficient over here. First, let's just put in our power handling. We want a minimum of 4 watts. So let's put 4 watts and then go all the way down to the bottom. Hit Shift and select the last one. That'll select everything from 4 watts to 100 watts. It's okay. The higher wattage resistance is going to cost more, but it's also going to be able to shed the heat better, which means it'll be a much more temperature stable resistor. Okay, the next thing we wanted is we wanted anything that in the temperature coefficient that was better than 100 parts per million. So we're going to select this guy all the way up to this guy. I guess I got to select them all. And we got 49 results. Okay. Last but not least, we want everything that says non-inductive, 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 non-inductive. I think non-magnetic. No, it's got to be non-inductive. Then we're going to apply all. Okay, we're down to 7 resistors. Let's see what we've got. Okay, these I've already purchased and already have sent to me. It's 5%, 25 watts, but it's got excellent 50 parts per million per degree C, which is twice as good as what we need. It's 25 watts, which means it'll help shed a lot of power very easily. Okay, and so that we can go down to 50 parts per million. Let's get rid of everybody that's above 50 parts per million. Okay, that means it's minus 20 parts per million if the temperature goes down, and it's plus 80 parts per million when the temperature goes up. Let's just pick the 50 parts per million. Let's get the best we can. Why not? Okay, we're down to 3 results. Let me slide back over. All right, so we have the options here. These are all 39 ohm, which is perfectly fine. And we have this ohmite one. Okay, I'm not too worried about this. This is 20. The other ones have higher wattage, which is nice. They're all non-inductive, which is good. These are moisture resistant, which might be good. And this is intentionally designed as a current sense resistor. That's exactly what we're using it for. And these have slightly better temperature range. So we have our choice between this guy and this guy. This guy costs $7. This guy costs $21. I think this guy is more than sufficient for our purposes, and that is in fact the one that I chose, and we have 10 of those in stock already. So that is the one we're choosing. 39 ohm, 5%, 25 watt TO220, non-inductive with 50 parts per million, temperature stability coefficient. Okay, so that's the part we're going to use. Okay, now we're going to go look for the transistor. Okay, coming back, now we're going to look at the things we need for the transistor. Well, we're going to look for an N-channel MOSFET, and the current that's going to go through the transistor is going to be, worst case, is going to be 12 volts divided by the 40 ohm ramp resistance, which is 0.3 amps. Okay, but in case we want to upgrade to a smaller resistor in the future, let's give us some margin and make that a 0.5 amp current handling of the transistor. All right, since our VCC is going to be 12 volts, we want a transistor that does better than 12 volts, so a minimum of 15. We don't want to go too high in the voltage, because the higher you go in the voltage, the more your input capacitance of your transistor is going to go up. So we want to keep the power, the voltage handling of the capacitors of the transistor as low as possible. So we're going to pick nothing more than 15 to 20, not more than 25 volts. Okay, now what's the power handling? Well, our short circuit condition is going to be limited by the resistor here. Okay, and so our power is going to be the current squared. Okay, so if we're going to go for a half an amp, so half an amp squared is 0.25 times R, which this R here is the resistance of the transistor. So it's 0.25. So it's 0.5 squared, which is 0.25, times the resistance of the transistor on. So we want to make sure that we want to keep this low. We want to make sure our resistance is less than 1 ohm. Less than 1 ohm. So the on-state resistance of our transistor will be less than 1 ohm. We're definitely going to do better than that. Okay, but that'll keep our power handling under a 1/4 watt if that's 1 ohm. So we were looking for a transistor that can do a 1/4 watt or more of power handling. So we want a power rating greater than a 1/4 watt. So let's go off to DigiKey and select our transistor. Okay, now we're going to select the transistor. So if you go to their product index, discrete semiconductor products, you want to go to transistors, and then we want MOSFETs, singles. Okay, we want in stock, active, and channel. And just that will drop us from 44,000 to 7,500, so we can apply there. Okay, so now for our continuous drain current, remember we wanted 0.3 amps, but that was our design limit. We want to use a transistor that goes from 0.5 amps to higher. So we're going to put that continuous drain current from, I don't know, 0.5 to, where's 0.5, 0.5. Okay, up to, I don't know. Let's just go all the way up to, not limit ourselves, go all the way up to 3 amps. I'm holding down the shift key, and that selects the upper range. I apply, that drops us by a factor of 10. The number of devices. Okay, the drain to source voltage, we want, well, we're not going to work at 12, so we're going to pick 20 and maybe 25, just to give us a little extra margin there. Okay, now the drive voltage. Well, let's actually look at the threshold voltage. The higher I have to drive the voltage before the transistor turns on, the more of a ring I'm going to get. So we're going to want a threshold voltage that's quite low. And so we're going to pick the one at the bottom, And we're going to keep this below, I don't know. Let's keep it below 1.8 volts. No, let's keep it below 1.5 volts. I'm holding down the shift key, and that selects the range. That drops me to 102 results. Okay. Now, the next issue is the input capacitance. We're not going to put a limit on that right now. What we're going to do is just go down to the table, which is built down here, slide over to the input capacitance, and we're going to sort it from min to max. Okay, and the device that comes up with oh, that's interesting. These didn't come up last time. Interesting. Oh, yeah, we want to try to keep the input resistance RDS on below an ohm. So we're going to pick 30 milliohms, which is the first, all the way up to, I'm going to hold down shift. Okay, so we want to keep it below an ohm. Okay, and that would put our preferred device as first. I already have bought 1,000 of these. When you buy these in lots of 1,000, they're 6 cents each. You buy them in 10,000, they're less than a nickel each. The problem with these devices is that they're very, 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 very tiny. These are less than a millimeter on a side. Okay, so the distance between the solder plates, the solder pads, is so small we're not going to be able to prototype with this per se. We'd have to get a professionally made printed circuit board. And we're likely to do that anyway. And if we do that, this is the transistor we will use. Okay, but for prototyping purposes, I need something that's a little bit bigger, and so it's easier to make a simple prototype board with. And so what I'm going to do up here is I'm going to go select a larger package. Okay, so I'm going to go pick SOT 323 is good. SOT 323, 23, 23, 23. I'm going to move my coffee cup. Hold on. This, that, I think those are okay. All right, let's see what we end up with. Okay, this 3134 comes up, but one of the things that I don't know why it comes up, because it says its power handling is 180 milliwatts. I'm very sure that we chose a power, oh, I guess we didn't put the power dissipation in. Okay. So we want to put the power dissipation, what did we say, a half a watt or more? Or was it a quarter watt or more? Let's put a half a watt or more. Okay, so what do we finally get on the top here? There we go. Oh, this damn thing. Okay, so the PJA 3434 is our transistor for prototyping purposes because it's big. It's a SOT 23. It can handle 750 milliwatts, which is a lot more than we need. I'm sorry, milliamps, more than we need. It's got a low turn-on voltage. It's got a reasonably small input capacitance. The other guy we picked before only had 33 picofarads, so this is twice the picofarads, but it's still down low, which is, and it can handle a half a milliwatt of power. Okay, so we're going to prototype with the PJA 3434. I've already purchased 1,000 of these because this is the one that came up last time I did this, so I've already purchased these. They're already in stock. Okay, and that is how we select the transistor. Again, just so you remind, we have two transistors. We have the one I'd like to use, but it's too small to use in a prototype. It's more of a, I need to make a professional printed circuit board in order to use it. And then I have this one, which is okay, it's in the ballpark. It'll still probably do very well for us, but it's big enough that I can make a prototype printed circuit board using a Dremel. Okay, and this may actually be the one we use. The difference is, okay, these guys in lots of 1,000 are, I guess they're not that much more expensive. They're kind of in the ballpark when you buy them in quantities. How much did I spend for 1,000? So 1,000 of them is 7 cents each. This may end up being the one because it's much easier to manually prototype these. The other ones actually, if we're going to do a production run, the other ones would probably be better off being machine placed because they're very, very, very tiny. Like I said before, they're almost as tiny as a grain of salt. Okay, so this might end up being the one for production. There's only 2,000 of them left in stock, which is really interesting. Let's see what the other guy is. Okay, they got 30,000 of them left in stock. So if we're going to do a large production run, we're probably going to use these. Yeah, I paid 7 cents a piece for them. Okay. You know, we can probably buy them in bigger lots too for 4 cents a piece. You know, if this thing takes, I doubt it's going to take off it, but this is just a demonstration to prove the theoretical model. I don't see this as becoming something that everybody's going to want to follow, but, you know, let's keep our options open. Okay, so that ends this little section of determining the transistor that we're going to use. Okay, the final consideration is how to hold the inductor under test, or the device under test. I wanted to mimic the Kelvin lead configuration of the Agilent LCR meter, so I could use the Agilent LCR meter attachments and the fixture I made for the thesis to measure the inductors. The problem with it is that this fixture, the distance between the actual measuring circuit, which will be back here, is about 4 inches. So I'm adding 4 inches of length, and I'm not sure that's a good idea to do for the CRIM circuit because this adds a lot of inductance in series with the inductance you're trying to measure. Now, granted, we can normalize that out, okay, but the problem is we're going to be measuring 100 nanohenries, and I'm pretty sure this fixture is going to have a lot more than 100 nanohenries, or something close to it anyway. So I'm not going to go with this method. Now, the important thing here is these inductors that were made for the thesis are the ones that we're trying to measure. And they all have this same footprint as far as terminals. These are brass screws that have been soldered to the pads. And we're going to, okay, so we are going to mimic this ability using little brass tubes as the coupling, but how these get coupled to the circuit, I'm still wrangling with that. Okay, and one final note, as said before, real inductors are more than just inductors. Okay, just as inductors have parasitic capacitance, there's also resistance. Okay, because wire doesn't have zero resistance, especially not the wire we're using. So what we have to do is we have to account for the resistance of the wire as well if we want to get a very high precision measurement. And so what we're going to do is we're going to add a resistance in series with our inductor. This resistance represents the series resistance of the inductor. Okay, and so now the voltage across the inductor is going to be the time change of current through the inductor times the inductance, and the voltage across the resistance is going to be the current times the resistance of the inductor, and that will be the voltage across the resistance. I'm using a lowercase r to represent the resistance across the inductor, and an uppercase r to represent our ramp resistor, our current sense resistor. Okay, so the total voltage across our inductor with its parasitic resistance is going to be VL plus VR, and we're just going to add these together. Now I'm getting rid of this minus sign here again. Don't need to carry around this minus sign because we're more worried about the signals, not the direction of the signals. that's not a big issue right now. So I don't want to carry this minus sign around. We don't need to carry it around because we know the directions of the voltages and the currents that are going to appear here. So now one of the interesting things about this problem here is this voltage now is a function of the current change plus the actual current. So this is what we call a differential equation, because these are different orders of differential representations of current. Now this beautiful mathematics called Laplace transforms is the most perfect thing to use for this. And Laplace transforms allows us to move all this stuff. This is in the time domain. So this current here is the representation of the current as a function of time, current as a function of time, and this is the voltage as a function of time. The way Laplace transform works, we move this from the current domain into the spectral or the frequency domain. And so we're going to transform this into the spectral domain. Okay, constants transfer over no problem. Okay, your functions as a function of time transfer as a function of time to a function of spectrum. And because this is a derivative of your function of time, you transfer the function as a spectrum and multiply by s to represent that this is the derivative of that spectrum. Okay, and your voltage in transfers over from the voltage in as a function of time to the voltage in as a function of spectrum. Okay, now this voltage in is the voltage across this. I don't want to say voltage step because the voltage step is going to end up as a constant. So this is the voltage as a function of time. It's not a constant. And here it's a voltage as a function of spectrum. Now the beautiful thing about converting this into a spectral equation is to solve the differential equation, all you have to do is solve for what you want, like using regular algebra. So we want to solve for the current in this circuit, and that works out like this. The next thing we want to do is we want to determine our input voltage as a function of spectrum. Okay, because we're applying an input voltage, this voltage starts, and then at the time t equals 0, this voltage goes to a constant value v step. Okay, and the way you represent this as a spectrum, this v in as a function of spectrum, is your constant value v step divided by the spectral operator, or the Laplace operator, whatever you want to call it. Okay, so now we're going to replace this v in as a function of spectrum with our proper input to the inductor as a spectral input, and we're going to replace that. We want to find the voltage across the resistor, and so you multiply your resistance times your spectral thing, and that's what you end up here with. So this is our spectral, the voltage as a spectrum across our ramp resistor. Now what we need to do now is, so that we can convert this into measurements that we can make with a scope, we have to do the inverse Laplace transform. We do that by going to a table. And so we go to the CRC math tables, 28th edition. We look at 12 is the perfect fit, because here we have S plus R, and this would be our S plus A, where A is 0. So I'm going to show you step by step, because when I taught this in college, it's just amazing how it's so simple once you understand it. So we want to adjust. We're going to take our value here. The first thing we want to do is we want to get rid of we want this S to be alone, because over here this S has to be all by itself. So we're going to divide top and bottom by L. So the top is going to be R, V step over L. These are constants. Okay, and then that, by dividing the denominator by L, makes the S in here alone, and this ends up being R over L. Okay, the other thing we want to do is move this off to the left so we can leave a 1 here. And then we want to make this S plus 0 here, so that we can get this spectral component of the equation matching the form in the book. And so what we can see from this is that our constant A is 0, and our constant B is minus R over L. And because this is a constant, this is the same in the spectral as it is in the time domain. So what we're going to do now, I'm going to go to the next step, is we're now going to take our values for A. We're going to bring down our constant because we're still going to use that, and then we're going to multiply our constant times the transform part. So this is the part we had on the left, and this is what we're going to replace it with now that we know what A and B are. Okay, and so this is 1 over A, which is 0, minus B, which is minus R over L, times e to the AT, A is 0, minus e to the BT, and that's what we get. And then when we reduce it all down, this is just algebra, we end up with, that is going to be our voltage over time across our resistor. So that, again, I'm going to reiterate what happens. We had a differential equation in time, and Laplace transforms allow us to convert our equation into the spectral domain. In the spectral domain, differential equations are handled like algebra. And once we solved for the variable we want, which was the current across through the system, once we solve for that, then we can transform back to the time domain, because the time domain is how we're going to measure it with an oscilloscope. Now, I've gotten to this point before, but this is why I love making videos for my Patreon followers, whatever, is because I missed, when I do this slowly and carefully, I end up seeing things that I don't see when I'm rushing to get it done. And this just flew my mind because I've already started to write software that would take simulated measurements and deduce the inductance using by selecting an inductance and select it with a known resistance and trying to match a set of simulated measurements. I was not very happy with that. But when I did this thing, I saw this nice and clean like we have it now, and then I had an epiphany. That epiphany is I can just solve. So if I take the natural log of both sides, solve it, and I can solve it. And this turns out I can actually take one measurement at a point in time and get the measurement. There's no ambiguity here. This is very deterministic. Okay, and this interesting thing is we're going to measure the resistance of the inductor with an Agilent precision LCR or precision LCR meter or whatever. So we're going to have a very high, better than 50 parts per million measurement of the resistance of the inductor. We're going to have better than 50 parts per million measurements of the ramp resistor. Okay, and the ramp resistor isn't going to change more than 50 parts per million with temperature, so it's going to be a very good, that's going to be a very well-known resistor. The voltage step we're going to calibrate with our 6.5 digit Agilent digital multimeter, so that step will be very precise. Okay, and then our time base is going to be very precise because everything we've gotten all our time bases down to better than 10 parts per million. Okay, the Achilles heel of this entire measurement is that our scope, this will be our scope measurements right here. Our scope measurements are only from an 8-bit scope. Okay, because in theory, if we could get a better than 50 part per million measurement here, we're going to get well below, and this will reconcile and converge very quickly. But because our scope only has an 8-bit measurement precision or accuracy, that's our Achilles heel. And I'm like, okay, let's see what it's going to, since that's going to be the limiting factor, let's see what it's going to do. So let's do some simple math. So we have an 8-bit measurement. By their nature are 1 part in 256 accurate. Okay, which it works out to 4,000 parts per million. That's not too bad. That's about twice the precision we're looking for, but of course we're not accounting for noise here. So let's just see if we can't get our goal to 2,000 parts per million or better. And I said in our thing that we're going to try to put 250 measurements on the ramp. Okay, but let's say we roughly break that down. We're only going to give it half of that. So that would be 128 measurements on the ramp. Okay, just to make this is a nice round number for reasons you'll see why in a moment. And one thing we know from doing measurements and metrology is Each doubling of a sample improves the signal-to-error ratio, sometimes called the signal-to-noise ratio, by the square root of 2. So 128 is nice because 128 is 2 to the 7th power. And therefore, our signal-to-error ratio improvement is going to be square root of 2 to the 7th power, which will be 11.3. So our accuracy with 128 samples, we take our 1 part in 256 times 11.3, which gives us 1 part in 2900. This works out to 345 parts per million, or about 6 times better than what we're shooting for. So, in theory, with an 8-bit scope, we should be able, as long as we take care of the noise, we should be able to get at least 6 times better than our goal of 2,000 parts per million. So it should be doable with an 8-bit scope as long as we can put at least 100, 128 samples. But as we said before, we're going to put 250, so it's actually going to be better. Okay, but in case, I'm looking into options because they do make 12-bit scopes. Siglent makes one for $5,000, and then they have one for Teledyne LaCroix for $1,400, and you do not want to know how much a Keysight or Tektronix costs. They're in the 20s, I think. That last I checked, they were anyway. Okay, but if you have a 12-bit measurement, that's 1 part in 4096, which is 250 parts per million. So it's interesting that a single sample from a single 12-bit sample of your ramp will get you better than a 250 part per million measurement. Of course, we're not accounting for noise now. That's going to be something we're going to have to deal with. That's part of what we have to work on next. Okay, there's also other options. In stock, I have 14-bit, not 12, 14. Okay, so this would be, we would be getting down below 100 parts per million in our measurement with a device like this. So this is wonderful. We have these in stock. I think we have 10 of them in stock. Okay, but they also make, for about $300, dual 14-bit, 250 million sample per second. Oh, let me back up. These only do 65 million samples per second. That would give us 6 samples on our ramp, which is completely doable. Okay, but again, this is a lot more work than just buying a scope, but it might actually end up being cheaper. Okay, if we do go that route, I'll probably end up purchasing one of these dual 14-bit 250 mega samples per second instead. We'll see. We'll see how the numbers work out. These are about 6 times more expensive than the A to D converter I just showed you. But again, we're going to getting 14-bit, which works out to the 14 reciprocal. So that works out to 60 parts per million with a 14-bit measurement. Okay, so we're down in the noise right there, which might just end up helping us out. Okay, so that's a possibility. It might be worthwhile to do this. I couldn't find anybody that makes a 14-bit sampling scope. I didn't look too hard, so if somebody finds one and it's, it can do at least 60 million samples per second, that might be an alternative, as long as it's inexpensive. Okay, so the wrap up, it seems like we will achieve the desired precision from the present plan to use a inexpensive 8-bit scope. We'll be exploring the Epiphany during the week using simulated data to see how it compares to the regression algorithms that I have already presently developed, which I was going to display this week until the Epiphany showed me that that's a better way. Okay, and the last part I'm wrangling with, as I described before, is the fixture or the means to hold the device under test. I would like to use the standard Kelvin lead configuration, but that may require more engineering, and I want to get answers quickly so we can get on to the cosmology series and do all the interesting cosmology experiments, and also the magnetic experiments. Thanks to my Patreon subscribers. I purchased a lot more components in stock because what I'm seeing that the chip market is drying. Everyone says the chips are easing. I'm not seeing it. I'm seeing high-end microcontrollers. The dates that you can get them are now being pushed off into 2024. So the ones I've acquired have been very prescient. I guess that's the right word, because we got them in case we need them. And this is going to be my weekly thing that if you go on DigiKey and you look up 32-bit microcontrollers that are more than 200 megahertz, okay, and that's the ones that are available. That's the ones that they have that are active, and those are the ones in stock. So this is going to be my metric. This seems to be the smallest number I've seen, and every week we're going to look at this to see what's going on with the market, whatever. So thank you. Sorry this is such a long-winded video, but you can see there's a lot of work going on behind the scenes here. I apologize that I can't get the videos done quicker. There's just a lot of work to be done. But I think my Patreon folks really understand that, and I appreciate that. Thank you.